Hello everyone. So today we are going to look at the concept of something called as a material derivative or a total derivative. This is in the context of Eulerian and Lagrangian descriptions. So far in our studies of particle mechanics and all, we have looked into kinematics which are described in terms of particle motions. So if we can track a given particle, the particle moves through space, and during the evolution, if we track the particle, we get something called as a trajectory. The trajectory is defined with respect to a fixed coordinate system, and each location is represented as x vector, which is essentially x, y, z. So suppose the particle started at x vector 0, which is x naught, y naught, z naught, and because of some kind of force field acting on it because of some other influence, it's going then at location x1, which is at a time t1, this is at a time t0, and so on. It is at a location xn at a time tn. So the trajectory is defined in terms of the coordinate x, which depends on the time and the initial location. So if we define if we write something like this, it means it's a function of time, and additionally one must specify the initial condition. Okay, so in this description, the velocity we know is given by the rate of change of the position, and the acceleration is given by the rate of change of velocity, or equivalently d2x vector dx dt2. So just to be clear, v vector dx vector dt is the same as u equal to dx dt, v equal to dy dt, and w equal to dz dt, or in some other notation it is also equivalent to u1 equal to dx1 dt, u2 is equal to dx2 dt, and equivalently u3 is equal to dx3 dt. So these are all equivalent notations of representing the same thing. So proceeding on, in typical fluid mechanics experiments, if we have a domain like this, where there's some kind of a inlet flow and some kind of a exit, and then there's some barriers in between and so on. So fluid enters here, maybe it hits the barrier, it goes out, or something like this may happen, or something like this may happen, and so on. So if we try to track each particle, it's incredibly cumbersome. Particles come in, traverse this path and go out, and then at the next instant the particle may come in, and depending on whether or not the inlet flow is steady or something like that, this trajectory may be different from the earlier trajectory and may go at a different path and so on. Okay, so in that case it is easier to describe everything in terms of fixed location in space at various times. So we'll fix a location and see how the variables of interest are changing in time. We'll see how they evolve in time. Okay. So the key idea is we have to somehow relate the Lagrangian and Eulerian descriptions. We have seen already that the Lagrangian description depends on the time and the initial location, while the Eulerian description only depends on the location and the time. So let's say we are trying to focus on a quantity f, which in the case of the Lagrangian description depends on where the particle is. So this gives you the location of particle at time t, which initiated at t0 at x0. So f is the quantity at this particle location, and similarly in time at this given location, f of xt simply defines the Eulerian description. So this is the value of f at x in the domain at time t. So the key idea is, when the Lagrangian and Eulerian frames coincide, then the quantities are equal. So f from the Lagrangian frame is the same as f from the Eulerian frame. Okay, but f from the Lagrangian frame is x is the f at the given location of the particle, which depends on time and the initial condition, and f Eulerian is simply f at that location at a given time. So say this is our Eulerian window where we are monitoring the variable f. So we continuously try to monitor this, and the particle is starting here, it goes, so at t equal to t naught, this is the location, so this is x0, which is essentially x0, y0, z0. So then the particle goes like this, and if at a time t it coincides with the Eulerian, at t Lagrangian and Eulerian coincide, the frames coincide, then the two things are equal. Okay, that's the key idea. So let's proceed. Let's say we have a so the location of the particle at a time t is here at x. Okay, this is the location of the particle, and at time t plus delta t, the particle reaches a location x plus dx. This is at t plus, so let's call it as delta x, and it's at a time t plus delta t. Okay, so we want to note how f evolves. So f at x plus delta x and t plus delta t is what we obtain when the particle moves from this location. So here it was f at x and t, and here it is f at x plus delta x, t plus delta t. Now this is essentially f at x plus delta x, y plus delta y, z plus delta z, and t plus delta t. Now we do a multivariable Taylor series expansion. So in this Taylor series expansion we have the contributions from these three spatial variables and this temporal variable. Okay, so we have f at x plus delta x, y plus delta y, z plus delta z, and t plus delta t is equal to f at x, y, z, comma t plus del f del x delta x plus del f del y delta y plus del f del z delta z plus del f del t delta t. So this is z. So the idea is that if we have a variable phi at x and we want to represent phi at x plus delta x, we have phi at x plus delta x is equal to phi at x plus del phi del x at x times x plus delta x minus x plus del 2 phi del x2 1 by 2 factorial x plus delta x minus x whole square and so on. So this is essentially delta x. So this is like the first order. So this is called the leading order term and this is called as the first order term. So this whole term is the first order. This is the second order term, because this is, so this term is called as first order because it depends on delta x. This is called the second order because it depends on delta x square. This is called 0th order because it depends on delta x raised to 0 and so on. Okay, so this is a standard notation that you may probably know from Taylor series expansion and all those things. So we have essentially then f at x vector plus delta x at t plus delta t. So I've gone back to the standard compact notation because I don't want to write x plus delta x, y plus delta y, z plus delta z and so on. This is equal to f at x vector comma t, basically this term, plus del f del x delta x plus del f del y delta y plus del f del z delta z plus del f del t delta t. So now we take everything to the left hand side. Not everything, but we take this guy to the left hand side and divide by delta t. This will be equal to del f del x delta x by delta t plus del f del y delta y by delta t plus del f del z delta z by delta t plus del f del t. And then we take limit delta t tends to 0. So look, the idea is in the limit delta t tends to 0, this location tends to this location. Okay, so essentially the two frames, so this was the this is the Eulerian frame where we are fixed and the Lagrangian particle has moved, but because delta t tending to 0 is tantamount to this Lagrangian frame going back to the Eulerian frame. The Lagrangian frame tends to the Eulerian frame. Okay, and so in that limit this thing right away becomes the rate of change of f, because rate of change of f in the standard Eulerian in the standard Lagrangian frame is f at t plus delta t when seen from the particle frame minus f at t. So this simply becomes df dt. So this thing is simply the Lagrangian derivative, because it is f seen by particle at t plus delta t, and by virtue of flow the particle is going at x plus delta x at t plus delta t, but essentially f as seen by the particle becomes f at t plus delta t as it goes from one point to the other. This minus f at xt minus f at t divided by delta t in the limit delta t tends to 0 is df dt in the Lagrangian. This is equal to limit delta x by delta t is the velocity at this point. The delta x by delta t tending to 0 is like the u velocity at the Eulerian frame. So if you look here, this was the Eulerian frame, and the rate of change of x at this location is the Eulerian velocity. So this is equal to del f del x into u, and then similarly del f del y into v plus del f del z into w plus del f del t. Okay, so essentially we have the Lagrangian derivative on one side and two groups of terms appearing on the right hand side. So both of these combined give us the Eulerian derivative. It is also the material derivative, substantial derivative, or the total derivative, and it comprises of two distinct terms. This one is called as a temporal term, and this is called as a spatial derivative. So it all stems from the fact that as delta t tends to 0, the Lagrangian description is tending towards the Eulerian description. Okay, we had a particle here which goes to this point from x at time t to x plus delta x at time t plus delta t. As delta t tends to 0, the Lagrangian particle is tending towards our Eulerian frame. Okay, so this is the Eulerian frame, and hence in the limit f at t plus delta t, so in the limit delta t tends to 0, f at t plus delta t minus f at t by delta t represents nothing but the Lagrangian acceleration. Hence on the left hand side we have obtained the Lagrangian acceleration, because the particle, so the quantity f noted by the particle at t plus delta t is naturally at x plus delta x, because the particle has moved from x to x plus delta x. Hence this naturally appears, but this is more relevant for the Lagrangian derivative. So f at x plus delta x at t plus delta t minus f at x comma t by delta t gives us the Lagrangian derivative. But because the frames coincide, this Lagrangian derivative has to be equal to this term, which is the Eulerian derivative. Here we are fixed, we have fixed our frame. In this sense, we have related the Lagrangian derivative with the Eulerian derivative. So to summarize, the total derivative df dt is equal to del f del t plus u del x of f plus v del y of f plus w del z of f, which equivalently can be written as del f del t plus u1 del x1 of f plus u2 del x2 of f plus u3 del x3 of f. In an even more compact notation, we can write this as the following: d dt of f is equal to del t plus u1 del x1 plus u2 del x2 plus u3 del x3 of f. So this is like the total derivative operator. So here we remember that u1, u2 and u3 are the x, y, z components of the velocity, and x1, x2, x3 are x, y and z respectively, in Cartesian coordinates at least. In an even more compact notation, d dt of f may be written as del t plus u summation of ui del xi of f, where summation of I is over 1 to 3. In the Einstein notation, if we have summations like this, we can drop the summation. So del t plus ui del xi f is the total derivative. Here the summation is implied. And because I is repeated twice, the summation is implied. I repeated twice. And there is nothing special about I, because I could very well be j, because I could have written summation I equal to 1 to 3 ui del xi as equivalently summation p equal to 1 to 3 up del xp, or summation j equal to 1 to 3 uj del xj, and so on. So it doesn't matter what index this is. This could be alpha, this could be beta, anything. The important thing is, if it repeats twice, you do a summation. You will see this notation in many books, but to avoid some, I mean, it's more convenient later on to use this kind of notation because it helps us write things in a more compact manner. But to aid understanding, it is comprised of this summation u1 del x1 plus u2 del x2 and u3 del x3 and del t. And this defines a total derivative. So it has a temporal component and a spatial component. So what exactly does do these components mean? So if a quantity f is to vary as it goes from point A to point B, in an Eulerian sense, the quantity can vary if the quantity here varies in time. So the quantity is located at a fixed location but changes in time. Equivalently, even if the quantity is frozen in time, it can change because of the actual variation of quantity in space. Okay, frozen in time but varies in space. Okay, so essentially it says that the weather change seen by a passenger going from Calcutta to Bombay is because of two components. The first thing is the weather changes because the weather is changing in time. So while the passenger is flying from Calcutta to Bombay, the weather is changing in time. Also the fact that geographically Bombay has a different weather than Calcutta. As we go from one place to another, the temperature, the weather also changes in space. So it has two changes, one in time and one in space. Okay, it's a very important concept. So please have a look again. Total derivative has two components, del t and the spatial ones. So given an Eulerian field, if you are given an Eulerian field, for example, if you have been given an Eulerian field u as, or let's say for now any Eulerian field f, x, y, z and t, then you simply do del f del t plus u del f del x plus v del f del y plus w del f del z to obtain the rate of change of f at that point. Okay, so sometimes it is also called as df dt to specify it's a total derivative. Okay.